we already covered the first item, coagulation and flocculation. I don't know whether you remember. One is related to organic compound. The other one is not. Which one is which? Do you remember that? Coagulation and flocculation. Coagulation, somehow you need to use inorganic compound. So what she is saying is chemically oriented. Yeah? And then what about the flocculation? It is more likely the physical in nature. Yeah, polymer, yes, correct. So coagulation, flocculation, wastewater treatment, mining, pulp paper, they use a lot. But what about pH adjustment? Here, this is a pre-treatment. So you have to adjust the pH or also the wastewater or the water treatment, the screening, and that's we considered as a pre-treatment. That's why. the sample of the diatomaceous earth, don't open it. That's carcinogenic material. Yeah. The other one, yeah, you can open it and look at it, that's fine. But don't open DE. Yeah? But they used to be really popular, still is popular. But recently they found out, hey, this one is carcinogenic. So don't open the DE. And sedimentation, centrifugation, filtration, thermal condition, dialose technique. So all of them are pre-treatment. We consider as pre-treatment. I'm wondering whether the chemical precipitation, that's, to me, something related to the coagulation and flocculation. We already covered that one, coagulation and flocculation. Certainly the purpose of early fine particle into larger flux for easy removal. The common agent, this is not, there are two of them. Yeah? Polyacryl amide, that's actually flocculant, right? Ferric chloride, aluminum, that's the coagulant. Also, you have to pH adjustment, optimize condition precipitation, coagulation, the mining, chemical manufacturing, and wastewater treatment. What about chemical precipitation? It converts dissolved substance in solid form of removal. Typical use, heavy metal removal, phosphate. The sedimentation, we already know about this, settling. Well, municipal water treatment, you see a bunch of the sedimentation. Screening is quite important for wastewater treatment, water treatment, for the industry as well. Degassing, deaeration, removal dissolved gas, CO2, beverage product, and heating, cooling. enzyme biological treatment, and ultrasonic sonification. Sometimes they use a surfactant, dispersant. Modify the surface tension, the surfactants are modified. But during the COVID season, the doctor recommend to use the soap and wash your hand. Wash your hand as well as you can kill the germ as well. Here, we are going directly to the, filter aid. The first one is diatomatic measures earth. I told you earlier. So don't open, and don't smell it, something. And this one considered to be carcinogenic. But they found out about 10 years ago, but previously they used this one without having any caution treatment. And then perlite and cellulose activated carbon, ashes. Currently, ash is quite popular, ash. But there are so much the impurity in the ashes. That's why we need to clean or separate something in order to use it as the filter A. Well, the sample that I gave you, some of them are black. Black. Anyone who actually traveled to Japan? Huh? But I really like you to pay attention to the when you go to beach. Our beach is white sand. Over there in Japan, beach is black sand. Black sand. Yeah, some of the filter came from Japan. Interesting is the wherever they go, I normally like my mount climbing. I try to go to the Fuji mountain. Surprisingly, all black. Not all, but they are black. However, now they can actually use as filter A. So here, ashes are less standardized than other filter A. Performance depends on their sources. Fly ashes. They are sometimes used as low-cost alternative. Compressibility affects cake permeability. Lower compressibility results in better. Then why you use the filter A? And ashes may contain toxic traces. I already explained to you about it. This is why. So actually, it's preventing the clogging the filter media quickly. That's why you have to use filter A. I don't know whether any particular without using the filter A. I doubt it. Almost all they use filter A. Hey, who found the box? That's a great idea. So improving filtration, reducing plugging, That's quite important one. Improving filtrate clarity, optimizing cake formation. Last one, extending filter lifespan. That's important. Is that title measures us? Yeah. It has a little bit of brown color.
Okay.
You're supposed to look at all the filtrate in filtrate. Sometimes you mix with the filtrate filter aid in the slurry. So once this one is in the solution, then you don't have to worry about carcinogenic. Only you have to worry about why it is dried acid, a dry form. A filtrate application technique, body feed, we're going to go over body feed and pre-coat as well. The cross-sectional filter press, making sure everywhere actually. See, this one is still number one. The cost is a little bit higher than the other. Still is, it works really well, that's why. Certainly, the filter aids are available different grade. Even though diatomaceous earth is same thing. There are so many different grades. So normally, smaller the particle is better filtrate quality, but trouble is the rate is lower. Then how can you find out which one is better? This is the equipment, capillary suction time. This is really simple equipment using the filter paper and then slurry and put some slurry into it, and then check the speed of soaking through it. So you can actually estimate filtration rate that way. I think I have a picture of that. Here. Oops. Yeah. Right here. This is a filter paper. This is slurry. And then check the timing. It's smearing into the filter paper. So this is not, but you can buy it, CST. It's not expensive at all. Plant or pilot trials should be conducted. Most data abrasive. So this is trouble. Filtered abrasive. So rice hull ashes, so when you look at it, something like this, right, surface, a lot of pores around it. Color is black from renewable resources, contain non-detectable crystals. And perlite. To me, this is the really good one. We use a lot perlite. It's really porous, popcorn-like. Unlike diatomate earth, perlite does not have microporous structure. Your solubility in earth is very low. Alkali solution depends on temperature and contact time. This is really common, known, most commonly used filter. In fact, the book, I actually add the diatomous earth, the picture there. I edited on it. So here, this is the issue right there. The filter A grade diatomaceous earth is crystalline type, considered carcinogen by inhalation. So if it is in the liquid, then you don't have to worry about it. The powder form is the troublemaker. The powder grade and the fiber cellulose is quite good one too. Disposable. Land disposable. Pre-cut. Body shade. I believe this one will tell you better. Same, no filter A, then clogging is issue. Once you add pre-cut, it's kind of schematic, not like that. Pre-cut protect the filter medium, prevent particles from bleeding through clogging the filter medium. It also enhances the cake release. Releasing wise, if you use pre-cut, it's a lot easier. Body feed, mixing the body feed filter A particle into difficult to filter material, particle change cake structure and reduce cake comparability. Last one, pre-cut plus body feed. The use of filter A is also called physical treatment. Mode of filter A application pre-cut, body feed, extend the filter time. That's we already discussed about this. Capillary suction time, we already discussed about this. Okay. So I believe this is the short presentation for the filter A. I really like to, I don't know, cover the membrane. What should I do? This is the last one.
Sir, can I ask you a question? It's like pre-coating on the filter. The filter rate is being pre-coated on the filter. isn't it?
And
We put, that means you are putting the coat on the filter beforehand.
yes, somehow, yes. Correct.
And body feed, like how are we going to use that filter?
It's combination mixed with the slur along with the filter. What should I do? Just
Now your lecture is till 10:30. So we can have 15-20 minutes more. Okay. So you want to start a new topic?
yes, and then once the time comes, I'm gonna stop it and it,
Okay, at 10:30 you are having tea break, and then we will go to industry.
yeah, and then
So
what I'm saying is
15
the
minutes left.
I don't know.
So mineral liquid filtration is in the second half.
Uh-huh.
Sir, wait.
Oh, yeah, it's okay. This topic is quite important one. You know why? The membrane usage is getting higher. Yeah? Even in the wastewater and water treatment, even though it costs a little bit higher, but the efficiency is so good. That's why membrane is getting popular. So somehow I like to let you know how the membrane made. So that's what I like to concentrate on. So yeah, this course you can actually learn how the membrane is produced commercially. Also, there are several different methods as well. Oh, this one doesn't know. What happened?
Sometimes it is not.
So this is kind of the bullet point. Membrane filtration serves a vital role not only in making water safe for human use, but in chemical, biological, and industrial applications, removing cells, cell debris, and other contaminants. See, here, first one, the particle filtration, uh, micrometer size, 10 micrometer, then you can use in any kind of the uh, screen, so you can also pre-filter some of the material. The Professor Mukhopadhyay, he brought that's probably good for particle filtration. Somehow it works for the microfiltration area as well, bacteria. So I don't know whether you notice or not. The red blood cell is quite big, Eh? The white blood cell is a little bit smaller than red blood cell, but the red blood cell is quite big. Bacteria and virus. So the ultrafiltration area is 0.01 to 0.1. Nanofiltration is 0.001 to 0.1. Reverse osmosis is 0.001. Then what about the filter media itself? If I want to use for reverse osmosis, then the pore size has to be less than 0.001. That's membrane area. Yeah? This kind of deputation, microfiltration, bacterial removal, and ultrafiltration, protein, virus, colorant. The end of this presentation, I asked to use the video. That video is going to be really interesting one. Ultrafiltration that is occurring in the kidney, in our body, kidney. So, yeah. The membrane, some of the membrane, the pore size is so small, so normally most of membrane we have to use cross flow membrane.
Some noise is coming. I want to adjust.
Okay.
Yes, yes, yes.
Okay. Yeah. But so when you talk about the membrane, you only use cross flow mechanism. Now, microfiltration remove the particle. Typical range is 0.025 to 10 micron. Ultrafiltration 0.001 to 0.05 micrometer. Reverse osmosis less than 0.001. Well, yesterday I heard that most of you already know osmosis, reverse RO. Who doesn't know about osmosis? Probably everybody knows about it. Huh? Anyone knows electrodialysis? This one is the membrane, a cation, anion membrane, cation membrane. So it's selective. You can filter out if the particle or anything that is charged. Now, I'm going into the membrane material itself. Polymeric membrane, polyether sulfone, PES. So good thermal, yes, the thermal is important one, PES. The last one, stress PTFE, of course. The thermal is concerned, this is a lot better than any other material. Polysulfone, polyvinyl, PVDF. This is quite important material. Now, however, this is a family of PFAR, like PTFE, which means forever chemical, forever. So That's currently the people are worrying about. And polyamide, cellulose acetate. Cellulose acetate used in reverse osmosis. However, for size has to be really, really small. In organic ceramic membrane, this is getting popular too. Alumina, zirconia, silica, titanium. Metal membrane, well, I don't know, it can go down to the ultra range, but certainly microfiltration, we can use metal. A composite membrane is multiple layer of the material. By the way, currently the media you see an innovative material, everything is multi-layer. Other advanced membrane, graphene oxide, carbon nanotube, and metal organic fragment. We're going to go one by one later on. This is the what I'm going to cover. Five.
10 minutes, maximum.
Okay. Solvent cast method, air cast membrane. In fact, solvent cast method is most popular. It has been. And stretch membrane, it is getting popularity. For myself, this is the future membrane. I strongly believe so. See, I checked the internet, the rating of membrane. You know what is the number one? I checked several different websites and checked it. Stretch membrane number one. Yes. 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 So I'm gonna go over one at a time.
That is different. PPP is different. Polypropylene, polyethylene, but that thing is very stronger, very strong. That is the difference because these are the other types of membrane packaging. Okay, PP, these are the other type of membrane packaging. So that is the commercially they are using.
What is the difference between media and membrane?
Huh?
What is the difference between media and membrane?
Same. Same, yes. Media is broad terminology. It is filtration material. It's called media. Membrane is small area of filtration material.
Membrane is one of the media.
Yeah.
Crystal media is a broad. Like you can have the media by metal also. You can make the media by ceramic also. It is one of the terms.
Yep. 10
5
minutes.
minutes.
Okay, here.
Membrane is only one-sided permeable.
It doesn't have to be.
One-sided? One-sided permeable means
only you can go from this side to this side, not this side.
that depends on the direction of flow. Wherever you put the membrane.
Okay.
Membrane is
See, certain membranes are asymmetric membrane. So you'll have to maintain the like as mentioned that multi-layer membrane. So you'll have to put the direction properly. Suppose it is not a multi-layer, it is a singular layer, then that doesn't matter. Wherever from the flow it can
Ajay,
Yes, sir.
are you trying to say about absorbing material?
No,
Or
no,
is it
sir, no,
filtration?
sir. Just for example, if we talk about osmosis, then it restricts the flow from this side to this side, even the flow is from one side to another. But it cannot pass even without pressure. We are not applying pressure from this side to this side, but it still restricts the flow from other side.
Osmosis is different. Normally osmosis is without the application of pressure. Okay, it is depends on the concentration. One will flow from one side to the another side. Whenever you are applying pressure of the higher concentration side, obviously it will work in the opposite manner. That is why the reverse osmosis came in picture. So nowadays the people are also going for forward osmosis. You are increasing deliberately the solute concentration, okay, and one side, so that the water can move from the pollutant side to the clean side.
One day, Professor Bajpayee had quoted that there is a difference between media and membrane. Membrane cannot be a media.
No, that is wrong. Media is everything. Media includes everything. Okay, that is wrong. Membrane, see, you cannot say that textile. You cannot say it as a textile media. That is one of. Textile media is the textile media which is made out of the textile media. Membrane is another category. It doesn't fall under the textile media. But you cannot say that it is not a media. It is also media, but it doesn't fall under the textile media. Textile media is whatever the material I shown you, that are all textile media. Filament, spun yarn, or whatever.
But polymeric media cannot.
If we are manufacturing electrospinning nano, can we say that is membrane?
Okay, then it is a, you can also talk it as that media also, textile media, because initially it is made, because it all depends on how it is being made. Suppose in some cases what the people do, making membrane, they make a sheet, simple sheet, without making the fiber. They simply make the sheet, they punch hole, okay, and then they expand it. Suppose if you are making process, manufacturing process is different, then it will be cannot be termed as textile material. Because you are making a sheet, you are punching, because the geogrid and some of the geotextile application, you can punch the hole, and then basically it is expanded in both directions, so that you can produce the hole. So it will be purely by membrane, but if you are making the membrane by electrospinning, for example, then it will come to the textile category, because you are making process is fiber. First you are making the nanofiber, then from the nanofiber you are making the membrane. So membrane can be textile based, also it could be non-textile based. Both is possible.
But polymeric membranes, I think we can consider in textile unless it is steel or the other
So if
ceramic.
it is simply a sheet, like solvent cast method, and if you are preparing a sheet, okay, initially, okay, and it is not a fibrous matter, and you are punching hole and then you are extending, expanding it, then it will be purely a membrane category.
Okay, here, everyone talk about the RO, but I don't know whether you pay attention to the media that pass through. The media is my concern. RO or osmosis. The media has to be, the pore size has to be really, really small one. Because you are talking about water molecules. Water molecule are going to pass through it, nothing else. So that is what we are talking about right now. That is membrane area. So this is quite popular membrane. PVDF membrane made out of this process. Most of the membrane made out of it. Well, it's a little bit older technology. But I don't know whether you notice or not. They use porogen. Porogen makes holes, hole structure. So you have to mix with the porogen. So the example of porogeneity here. This is structure of the solvent casting. Polyether sulfone is gradient density one, but the PVDF really great, the structure-wise. So I like to stop here. Continue after the trip, plant trip.
Yes.
Rest of the membrane technology. This one, we already covered that one, solvent casting, but this is really popular one. And next one, and this is the example of solvent casting. Next one is air casting. It's almost same, but it's not solution, but still they use solution. But somehow,
Is the solution made of solution that is correct for
okay,
evaporation?
it depends on the polymeric material. So PVDF is not really air casting.
Solvent cast membrane, right?
Huh?
PVDF is for solvent cast membrane, right?
Well, it's not, well, I don't know. Probably you see it. Air casting. Cellulose ester, right by cellulose ester membrane are made out of the esterification cellulose, typically using acetate and nitric acid to produce cellulose acetate and cellulose nitrate derivative. These membranes are widely used in laboratory and industry application due to their excellent chemical comparability, high flow rate, and low protein binding properties. Okay, this is my key interest. Key interest. Yes. Stretched membrane. There are two different stretch. One is dry stretch, and second one is wet stretch. So dry stretch, you have to make the polymeric sheet first. For instance, high density polyethylene, then you have to extrude high density polyethylene through the extruder. And then you have to make really thin film and not like sheet. Yeah. And then the other important thing is, first you have to stretch machine direction only. We call it MDO, machine direction oriented, MDO, machine direction oriented. So you have to stretch machine direction first. Normally, when you stretch machine direction, you have to apply the heat. Yeah. So the heat temperature is quite sensitive. So whether it's polyethylene or polypropylene, polyethylene probably around 100 degrees C. And polypropylene is a little bit higher, maybe around 120 or so. So it's right before melting point. You have to choose the right temperature and stretch machine direction. Higher the machine direction stretch ratio, the better. So it takes some skill, because once you stretch the width-wise, it has to be uniform across the width. Otherwise, the product you're going to get is not really uniform. So normally, machine direction stretch is quite important. Then transverse direction stretch. So here the polymetric film, machine direction like that. In fact, I didn't bring the actual picture of it. It's actually several rolls. Go over the roll and roll. So it's not like go to the stretch like that. No, it's not. So you have to set the individual roll temperature, precisely. So I should have brought some pictures. But anyway, probably number of rolls is about 6 of them. Go through six rolls. 1, 2 rolls, 3 rolls. Go over something like that. Not like this one. Not like this. This roll. The overall system, first you have extruder, and then you put the pellet, polyethylene pellet or polypropylene pellet into the hopper and extrude and make kind of thin, thick film first. And then you have to stretch. This one is not roll. Stretch as far as you can, and then make a little bit thin one, and then go through the MDO. MDO is machine direction oriented. Then we have to use so-called tenta. I'm going to show you later. Tenta. And then you can obtain the biaxial stretch film. That is I don't know why they call it the dry stretch, because polymeric material you have to melt and make the sheets or films, right? But they still call it dry stretch. Then what is wet stretch? When you make the PTFE stretching, EPTFE, expanded PTFE, then somehow you have to mix with some paste. So it's the isopar petroleum oil. You have to add it to it. So that kind of paste-like. The PTFE is really fine powder, fine powder. So from fine powder, somehow you have to make sheet. How you going to make sheet? Then you have to use some kind of oil. So isopar something. So oil. The other important thing is the raw material you have to store at the room temperature. No, lower than room temperature, because otherwise it crystallizes quickly. So storage, it has to be around less than important temperature is 19 degrees. 19 degrees is important. So it has to be lower than 19 degrees. Storage is same thing. The trouble is if we got some material, raw material, PTFA material from, let's say, China, then shipping, during shipping, the temperature going to go up more than 19 degrees. Then you have problem. So they have to put it in some cold box. Also, they have to control the temperature inside too. So the 19 degrees is critical. So they have to maintain less than 19 degrees. The putting with making paste-like material, and then we normally leave at the 19 degree, below 19 degree for 2 days. And then somehow you have to extrude out. Extrude out and make some sort of film. It's the same thing. After that, same thing. You're going through the MDO. That's why they use the wet stretch. They use some sort of solvent to make their paste. That's the difference. But EPTFE making that way. So wet stretch process is making expanded tetrafluoroethylene film. Here it is. This is actually TDO, not MDO. MDO has a lot of rolls, but this one is TDO, stretching, coming out and stretching transverse direction like this. See, most important thing is this one, clip. Clip is quite important. Probably about 20 years ago, they did use the more than inch clip, but nowadays it's a lot less than inch clips. So it's the quality depending on the clip itself, right here. Clip. Bruckner is still making it, but price is high. So you don't understand. Film goes inside and stretch. Here, this one. A little bit of the gray area, that is film. This is the, I already show you this picture. Look at this. This is 5 micrometer. What do you think of the single fiber itself? Let's say this is 1 micron. What do you think of? It's about 10. Yeah, yes, yes, correct. This one is actually desirable. However, I don't know whether commercially we can stretch like this. Okay? This is highly stretched material. So normally what you see is something like this. That is actually commercially available EPTFA. What? Pore? Pore size is probably around 0.2 micrometer. Yeah, pore size. I'm not sure though. Okay, this is actually this is commercially available. A dry stretched polypropylene extruded film. But quality-wise, it's a little bit issue, but it is available. But this one, the porosity is a lot. So normally EPTFA, the porosity is around more than 95% porosity. This one is around 60 or 70%. So porosity is.
It seems more porous in picture.
Ah,
Historically, it is more porous than the previous one.
I didn't get it.
The picture shows the more higher porosity of this as compared to the previous picture.
I don't think so.
PTFE. Maybe your resolution is higher in this case as compared to the previous.
Okay, here. That's the good question. Here, somehow you have to understand the fiber and fiber are not bonding each other. So it's one on top of the other. So porosity is more than 90%, 95%, something like this. However, this one, that one, the fiber is not like this, stretched. That's why the porosity is lower, a lot lower. But however, that is 1 micron range. So individual, this fiber inside is quite small. So, now, track etch membrane. This one, the Father, he mentioned about sometimes making the porous material, put some holes in it and stretch it, but this one doesn't stretch, but actually making holes in it. That's the etching process. So swift heavy ion make the holes so the polymetric film like polycarbonate, polyester, pores formed by irradiation or with high energy particles such as heavy ions, followed by chemical etching. The result is membrane with cylindrical pores of controlled size, shape, and density. So the track etch membrane probably porosity might be a lot less. However, the holes are really uniform. Just like that. So holes are really uniform. The pore size is over 10 micrometer to several microns. High pore uniformity, of course. Pore density control from sparse to very dense. High chemical thermal resistance to material and smooth. Good for microscopy and imaging. Certainly, you can look at the SAM pictures. This is, I don't know whether it's a popular process, I doubt it. Polyamide thin film composite membrane using TMC solution and MPD solution and PSF support layer and then polymerizer occur. and then making thin film composite membrane. Let me see what type of material. TFC membrane. Huh. This 30 micrometer still looks good. Yeah, this is the quite important message. Outside the layer, this is size comparison. The size comparison. So the ultra filtration range is right there. Then probably nanofiltration is down there. But the important thing is reverse osmosis. This one, pore size. Pore size is around 0.005 microns. The salt is around 0.007 microns. So if we like to use the reverse osmosis using some membrane, then the size, micron size, has to be less than 0.007 micron.
Excuse me, I want to raise the volume.
Raise it before? Oh, okay. So this is more likely coming through this one. It has to be something water molecule instead of calcium and natrium, something like that. I told you earlier the red blood cell is about 6 micrometer. It's quite big. So bacteria is about 0.2. So Na ion is going through flow rejected water. It's membrane like that. I think it's nothing to do with the RO. Huh? Probably a little bit.
The membrane element is
Shape of membrane filters. Membrane disc, circular, flat membrane, diameter about 13 millimeter, 25 millimeter, 47 millimeter, 90 millimeter. And then they do have a flat sheet membrane, pleated membrane, cylindrical, when inside the cartridge housing, hollow fiber membranes, bundled with the cylindrical. He already showed us. A tubular membrane, straight tube with a membrane lining inside or outside. Spiral wound membrane, flash membrane, wrapped around a central tube in a spiral. Capillary membrane, cylindrical, bundle similar to hollow fiber, but typically with a larger inner diameter. Here is some examples. Hollow fibers. This is the flash sheet. Yeah, flash sheet is right there as well. The hollow fiber combination. Yeah, plated flat media. We already seen this one. Probably you already see this one. Spiral membrane modules, 90%. So actually, the same membrane is making so-called multilayer. But important thing is permeate side, the mesh spacer. The mesh spacer sometimes control the overall pore size as well. Hollow fiber membrane. Spiral membrane. Started with filtration. It's more like the deactivate bacteria or viruses membrane. Some membrane does the kill the bacteria or viruses. The UV is really great. UV is really great. So probably they might use the UV similar type. This is the industrial membrane process. I think you already seen something like this. Membrane. Here, membrane module. This is really old picture, but still, some of industry you may be able to see similar to it. So, the membrane properties. What about porosity, pore size, mechanical stretch, thermal, chemical resistance, selectivity, permeability. Last one, comparability. Comparability with the solution that you want to use. So some of the solution may not be appropriate for using certain type of the membrane material. Fouling is a big issue actually. That's why they use the cross flow, generally shear flow. Rotation, vibration are also used to reduce fouling. Certainly, pre-filter is really important. Periodical cleaning is important as well. Now, go. This video is really good one. Really. I really like you to watch maybe twice or more. It's Columbia University made it. Oxford. I'm sorry, Oxford.
The kidneys are organs of the urinary system. They regulate the water content of the body and remove metabolic waste through the formation of urine. How does urine form? When blood reaches the glomerulus, it is maintained at a relatively high pressure. The high blood pressure forces water and small soluble molecules, such as glucose and amino acids in the plasma, through the thin walls of the glomerulus and the Bowman's capsule into the capsular space. This process is called ultrafiltration. The fluid that is filtered into the Bowman's capsule is called glomerular filtrate. The filtrate has a similar composition to plasma. However, no plasma proteins and blood cells are found in the glomerular filtrate because they are too large to pass through the walls of the glomerulus and the Bowman's capsule. After ultrafiltration, the glomerular filtrate flows through the kidney tubule. In the kidney tubule, useful substances in the filtrate are absorbed back into the surrounding capillaries so that they are not lost from the body. This process is called reabsorption. It occurs mainly in the proximal convoluted tubule. In the proximal convoluted tubule, all glucose, amino acids, and most salt are reabsorbed by diffusion and active transport. As many solute molecules are removed from the filtrate, the water potential of the filtrate rises. Therefore, water in the filtrate enters the blood by osmosis. The reabsorption of water raises the concentration of urea in the filtrate. Thus, urea in the filtrate diffuses into the blood. Further reabsorption of substances takes place in the remaining part of the kidney tubule. After reabsorption, the remaining filtrate in the collecting duct is called urine, which will be passed out of the body when we urinate.
Well, why don't you repeat one more? Because this is ultrafiltration inside our body. Oh, once more. Yeah, it's quite important concept.
The kidneys are organs of the urinary system. They regulate the water content of the body and remove metabolic waste through the formation of urine. How does urine form? When blood reaches the glomerulus, it is maintained at a relatively high pressure. The high blood pressure forces water and small soluble molecules, such as glucose and amino acids in the plasma, through the thin walls of the glomerulus and the Bowman's capsule into the capsular space. This process is called ultrafiltration. The fluid that is filtered into the Bowman's capsule is called glomerular filtrate. The filtrate has a similar composition to plasma. However, no plasma proteins and blood cells are found in the glomerular filtrate because they are too large to pass through the walls of the glomerulus and the Bowman's capsule. After ultrafiltration, the glomerular filtrate flows through the kidney tubule. In the kidney tubule, useful substances in the filtrate are absorbed back into the surrounding capillaries so that they are not lost from the body. This process is called reabsorption. It occurs mainly in the proximal convoluted tubule. In the proximal convoluted tubule, all glucose, amino acids, and most salt are reabsorbed by diffusion and active transport. As many solute molecules are removed from the filtrate, the water potential of the filtrate rises. Therefore, water in the filtrate enters the blood by osmosis. The reabsorption of water raises the concentration of urea in the filtrate. Thus, urea in the filtrate diffuses into the blood. Further reabsorption of substances takes place in the remaining part of the kidney tubule. After reabsorption, the remaining filtrate in the collecting duct is called urine, which will be passed out of the body when we urinate.
अगर आपका बच्चा सिर्फ मार्क्स ला रहा है और कॉन्सेप्ट
Yeah. Kidney, if some somebody has the kidney issue. Then in US, the same thing. We have to wait a lot. Somebody donate the kidney and then replace it. But scientists, especially Oxford, they are trying to make the man-made kidney using ultrafilter. Oxford. Using man-made ultrafilter material. Exact material is stretched membrane, EPTFE. Yeah, they tried several times, but it's currently not successful. However, they try to understand reabsorption. That's the issue. The ultrafiltration wise is okay, but reabsorption is tough. So, I believe maybe about 5 or 10 years later, they might be able to come up with the man-made kidney. So currently there are a bunch of patients who have.
Suppose it is filtration first, then it is absorbed. Why it is done this way? What is the reason?
Essential minerals.
Why it is done in a two steps? For example, you are removing something, then it is reabsorbed. Okay. Why it is done in a two step? Why it is not done in a single?
Retaining vitamins and minerals of the.
See, if you see the filtration, first filtration, glomerulus filtration, that is similar to that ultrafiltration. What happened during the removal of the urea matter is larger in size. It is larger. So whenever you are removing the larger one, smaller one like glucose, amino acid, that will be also removed. That is the main issue. As because you are removing the larger particle, smaller particle will be also removed. Now how to handle the smaller particle? Then it is reabsorbed. That is why it is second step process. Otherwise, why not single step process? That is the point. And people are also trying to make actual, replica of kidney. Okay, but it is not a membrane way. They are using the 3D, 3D bioprinting and tissue culture. 3D bioprinting and tissue culture. By having this combination, they are trying to develop the kidney in place of your, whatever the dialysis system, present dialysis system. But it will take a lot of time because kidney, the nephron is the unit of kidney. That is very complex organ. Okay. That is the problem. Nephron is not so easy.
Yeah, like I told you, reabsorption is key issue. So, so somehow they have to come up.
Absorption is basically biological phenomenon. Whereas the ultrafiltration, that is easy to replicate, but the biological one is very difficult. Whichever is biological. Reabsorption is biological. That is the main biology mixing up together.
Yes, that's why I really want you to look at twice. The reabsorption part is really important part. Well, normal person, they actually miss that. So, filtration-wise, I believe any university research, they can come up with a man-made material. And then, like he's saying that the biologically related, the reabsorption is so difficult. So I actually searched the ranking of membrane material several places. The future number one is EPTFE. So I'm keep telling everyone somehow somebody need to pay attention to it. Produced EPTFE. even though you start right now, it takes a time in order to produce a sellable material. Normally it takes 5 years. So start early better. So EPTFE is, first of all, it's inert. The other one is the temperature. It go up to 300 degrees. Up to almost melting point of the PTFE is 340, 300 degrees. The other thing is, this one, friction factor is low. So certainly it's the hydrophobic material, but you can still make it hydrophilic. Somehow you have to use the some high voltage, something, some other things. Told you last time, EPTF is certainly
For the environment,
huh?
is it sustainable for environmentally?
Yeah, I can tell you one thing. Currently, the PTFE or PVDFE, the membrane-wise PVDFE, the solution casting method of producing, that's a really popular one. So still it's everlasting material because it relates to the fluorine there. However, I don't know whether I mentioned about it or not. Enzyme development is quite currently active. For instance, the polyethylene-wise, the enzyme is already, I don't know, it's still under the development. But once you come up with the enzyme for certain polymetic material, then degradation is no issue at all. So I strongly believe that within 10 years, they can come up with some enzyme or put some branching into the PTFE molecules so that it can be biodegradable. So yeah, currently it's not. But to me, within 10 years, they can come up with some solutions for that. So I strongly believe the EPTFA is future direction. Yeah. Because pore size is small. Also, he actually mentioned really good question. Uniformity. EPTFA, you don't have to worry about it. You always come up with the same one. But solvent casting, that sort of thing, no, there is no way you can repeat over the time. And then uniformity across the web, that is key issue. So the solution is we can have biopolyethylene, biopolypropylene, biopolyester. However, once you polymerize it, then it's the same issue. Even though it has a bio in it, but it's not going to be biodegradable. So monomer comes from a little bit, the natural source. But the other one is petroleum-related source. That's the only difference. once you polymerize it, it's going to be the same. However, there is some issue. Carbon footprint. Carbon footprint is starting the material to end the disposable. So, first part of it is related to sustainable material, because starting with biodegradable material, right? But once you make the polymeric material, then it's the same as petroleum. But half of the size is the carbon footprint wise almost zero. So carbon footprint is concerned is a lot less. That's why people are quite interested in looking at in the biopolymers. So developing sustainable liquid filter media. First of all, eco-friendly material. They can filter liquid while reducing environmental impact. This field involves environmental engineering, material science, industrial process, tailoring, medical food, municipal water treatment. This is quite important one. This one actually I made it. I made this chart. Sustainable filter material, two categories. One is synthetic, the other one is natural. Synthetic material, biodegradable material, the PLA certainly is biodegradable. PHA, PVA, PCl, PVS, all of them are biodegradable synthetic material. Down here is a long-term degradable PE, PP, PET, bio-PE, bio-PP, bio-PET. But I didn't put EPTFE, PTFE there. Currently, it's everlasting material. I didn't put it at this moment. I can put it sometime later. What about natural material? So all of them, the cotton, jute, coir. You know what the coir is? The pineapple, not pineapple, huh? Coconut. Yeah, coconut. Hemp, rami, bamboo, lignin, viscose, canal, silk, wool, nanocellulose, metal, nanoparticles. So currently, in US, the same thing. My wife told me that you have a really nice bedspread, so made out of bamboo. So the feels really great, but there is the issue. The durability is not there. It doesn't go last. I normally when I sleep, probably my leg wants to move really a lot. That's my wife always complain about it. That's why one place we can easily make hole. But synthetic material, it never happened. Made out of bamboo that is the issue. Also, the cost is higher too. So synthetic material durability is a key issue to me. But feeling is great because it's the natural material. So to me this is this is one of the solutions. Hybrid between natural material with a synthetic material. So this slide to me is quite important one. No one has a, I need to pattern it. I don't know whether, I don't think so. But the natural material, mechanical durability, natural fiber, great. Wet conditioning pressure, so degrade really fast. That is issue. Quality, a lot different. Can be costly. Here, this is current filter media. That's what I'm like to talk about it. Huh? So once you read it, probably you may guess what material that is. So due to excellent chemical resistance, high filtration efficiency, maintaining low resistance, not zero resistance, because of its high surface electric charging characteristic. So polyethylene, polypropylene nanowoven material becomes standard material for filtration applications in air and liquid filtration. So polypropylene and polyethylene, how long it's gonna be survive? I believe, to me, at least 20 years or more. You know why? First of all, it's easy to process, making fine fibers. The other important thing is polyolefin. You can easily electrocharging. Charging is easier, a lot easier. So the current filter material, available in the marketplace. To me, the polypropylene is number one, polyethylene is number two. Is replacing by some material replacing by the EPTFE, but cost is too high. That's why it's not going to be that fast. Now, however, polyethylene and polypropylene, I believe it will stay more than 20 years from now. Here in US, I don't know about in India, every household or building, they have to use filter. Filter in every house. In my house, I have to change the filter every 3 months. Change it. Air filter. Air filter. Well, liquid filter as well. They actually use membrane. No, not membrane. Melt blown. A lot of those. Yes, melt blown. Water filtration. He showed you some sort of cartridge, round cartridge. A lot of those is polypropylene membrane, not melt blown material. Yeah. Also, 99% of face mask out of the melt blown material. Water filtration is polypropylene, the melt blown material. So the key issue is it's easy to charge the surface of it. Then what happened to the liquid side? Still its effect is charged not charged. So, not as great as the air, but liquid is the same thing though. But there are some biopolyethylene. I'm going to talk about this biopolyethylene terephthalate made from renewable raw material in the marketplace. However, these biopolymers are not always biodegradable, even though they are recyclable. That is a little bit of the issue. Then, how biopolyethylene, polypropylene, or biopolyethylene terephthalate can be made? So bio-based plastic man-made, man-processed organic molecule derived from biological resources for plastic and fiber application. What is public concerns? Environment, waste, pollution, and climate change, carbon footprint. Carbon footprint is a big issue. Bio-based plastic could reduce environmental impact and carbon. That is true. Carbon footprint-wise, plastic material helps a lot. Also, they are all recyclable. This is how the biopolymer made. The starting raw material is the sugar cane or sugar beet, garlic skin, cereal corn, agave. You know what agave? Agave is the raw material of tequila. Mexican tequila is made out of agave. And the wheat, that is what? The whiskey. Why I didn't put corn in it? Yeah? Oh, corn is there?
Seedlings. Besides seedling. Garlic skin and corn.
Yeah. The corn should be there. And because I came from Kentucky, Bourbon County, home of bourbon. So material. This is raw material. Then fermentation. Fermentation is quite important, and glucose end up with ethanol. Some of them are edible, but this one, it doesn't have to be edible ethanol. Even though it has a lot of the impurity in it, it still is okay. And then, the cellulose has a lot of different structures. Lignocellulose has a little bit. You need to look at the lignocellulose is a kind of cellulose, but it's a long chain. The chain is a little bit longer. So here, whiskey from Bali, bourbon from Icon, tequila from agave, for your reference. And then dehydration, then you can make bioplastic. This is the one of the example. Brazilian Braskem petrochemical company. Actually, the Braskem is associated with Dow Chemical. So currently, they produce the bio-PE. The raw material is the sugar cane. But the price is not really high, but it's 1.5, so it's a little bit higher than polyethylene currently available in the marketplace. So this is bio-PE, but the bio-PP, bio-PET is available. However, the process stays the same. So how to make the biodegradable plastics? Currently, most of the effective way make the biodegradable polymer seems to be biodegradable additives such as vinyl vinyl acetate, starch, pro-oxidant like iron, manganese, and cobalt, or UV stabilizer. This is the issue. See, most of the plastic material, the polyethylene, polypropylene, they do use a lot of UV stabilizer. UV stabilizer, yes, UV. So the one conference I actually suggest to reduce the UV stabilizer so that it can biodegradable quicker. But I doubt it. So if they reduce the UV stabilizer, sometimes UV stabilizer give you some the oxidation better. So anyway, this is the big issue currently. So all the big company, Exxon and Dow, they can reduce the UV stabilizer. Then normally polyethylene, polypropylene, it degrades a lot quicker. So to me, this is what I'm thinking of, not from somebody else. This is my kind of thought. Yeah. Appropriate enzyme development specimen. I believe this is key to me. Key. The last one is not easy one, the chemistry portion of it. So even PTFA, they can put biodegradable branch a little bit there, and then it can be biodegradable later on. So currently, the biodegradable testing, yeah, a lot of them. ASTM is key. ISO has some. But actually, when I read about it, it's not really biodegradation of plastic material. So it's kind of the short-term the testing. Somehow there are a lot of the missing portion of it, so they have to upgrade. Okay, this is the issue. PFAS. Here, polyfluoroalkyl substances. They call it PFAS. The last time when I was here, the person asked about the PFAS. So PTFE or PVDFA is under the PFAS. So somehow in Europe and Asia, there is some restriction on the PTFE and PVDF as well. The issue is this one. PTFA, there is no way it dissolves in the water. So it's really safe. But bad portion is still under PFAS. Now I'm gonna talk about something about the nano size, and then currently available the filter material. Show you. Certainly nano size, we already talked this one last time. So synthetic pressure drop wise is a lot lower compared with the glass. The synthetic media production, biaxial stretching, melt blowing, spun bonding. We already talked about that one. Penta is there. Also, I already show you this one as well. The melt blown. I also have the melt blown machine pattern, about 3 of them. So it really depending on the design. Then you can actually go down to 0.5 micron size melt blown. Normally, melt blown material, the fiber size has big distribution in it. So if the fiber size is, all of them are smaller, then pressure drop gonna fit. So combination of the fiber size, that's why pressure drop is lower. So it's polypropylene, certainly in water filtration area, they do use a lot. This one is a popular one. Yeah. So some of the fibers are really fine. Here, that is liquid filter made out of the melt blown. But air, they use a lot. How long? I strongly believe probably more than 20 years, I believe. Because there is no way they can replace this material. The price-wise, also the performance-wise. But this is the one of the big company in U.S. They are making money out of this product since 30 years ago. They are making the HVAC material called Interpret. So this is the spun bond material, but polyethylene and polypropylene combination of it. They also charge it. Also, there is some so-called triboelectricity effect too. What is triboelectric? Triboelectric is if you have two different fiber material, then rubbing each other, then it creates charge. So even though it has the surface electrostatic charge in it, along with during the process, it creates triboelectric charge as well. That's why this product has been popular. Also, it's spun bond, so the production rate is really high. So cost is a lot lower. There is no way somebody else compete with this product as far as cost is concerned. So this company is making bunch of money out of this process. The HVAC market is not really high efficient. It's kind of intermediate area. Also, liquid filter in not really high area like melt blown, but this is a lot lower than melt blown. But they do use this one. Well, this is the air filter, but all of them made of polypropylene. So electrostatically charged, expanded polyethylene interrupter currently for front of air filtration as well as liquid as well. Here, charged PP, charged PE, brand, EPTFE, the efficiency, delta P, fiber size, melting point. Yeah, look at this, melting point. EPTFE, 327 degrees. Actually, you can go up, it can go up to 304 operating temperature as well. Because the PTFE has really sharp melting point. That's why operating temperature, you can go up to 300. And next one is the charged PP and charged PE, P brand, and EPTFE. It's kind of similar, but when you look at the EPTFE membrane, 99.9 plus. So I strongly believe the next 10 years you will see a lot of EPTFE in liquid filter area. Durability was really great. Here, the electrospun material, the key issue is strength. So, electrospun material, you can use it in the air, but if you want to use in the liquid, then it has to bond with a certain material, really highly bonded certain material. You know why? Strength of individual fiber is really low. So once you rub it, it just becomes powder. Even you are rubbing slightly like this. That's why the electrospun fiber is tough to use in the liquid area. Yeah, I believe that they can use. So, current and upcoming air filter media. Number one. This is not mine. So you can actually look at it, the internet, and ask AI. That's the one. Then certainly come up with the number one. It is definitely. Efficiency-wise, pressure drop-wise, durability, and cost is the issue. It's a little bit high. Not a little bit. Sometimes it's really high. But efficiency is way up. Huh? What about stretched polyolefin? Efficiency is relatively good. Pressure drop, I told you earlier, since porosity is a lot lower than that of the EPTFE, so the pressure drop is low to moderate. Durability, yeah, normally is good. The cost is, I think it says high, but I don't mind, it's okay. And what about this one? Good ready. All of them, we use in the liquid area too. The current and upcoming liquid filter media. Number one is definitely rank right there. Ceramic membrane, the number 2. PVDF is number 3. Here, look at this. PTFE, PVDF, they are on the P5, but still it's number 3, number 1. Ion exchange media is number 5. Stretch polyolefin is number 6. So, the expanded polyethylene strength is exceptionally chemical resistance, hydrophobic, high thermal stability, very fine pore structure, low pressure drop. It has everything, good one. See, application, critical pressure, pharma, bio, they already use it. Even in the HVAC market, slowly the EPTF is replacing with some other polymeric material or glass material. So cutting edge use often use the high-end filtration, ultra pure liquid and gas. Yeah. Ceramic membrane is getting popular, and strength extremely durable, chemically, thermally resistant, long lifespan, backwashable, and highly fouling resistance. That is true. See, ceramic material, you can burn it and then reuse it. See, application, wastewater treatment, food, beverage, pharmaceutical, high temperature, cutting edge use, becoming increasing commonly in advanced water recovery or harsh chemical process. PVDF, this is quite the important one, even though it is a solution casting material, however, but it's quite popular material because of the strength, chemical resistance, good thermal property, excellent mechanical strength, application, ultrafiltration, microfiltration, filter, pharma, and water treatment. Commonly membrane bioreactor, MBR, we talk about it, right? It uses the PVDF membrane. Later on, probably they might replace with expanded polyethylene, the EPTF. I strongly believe that's going to happen really quickly. The PES, ether sulfur, this is high temperature polymer they call it, but not compared with the PTF. Yeah, good mechanical strength and the application in pharmaceutical, medical, and lab scale sterile filtration. Sterile filtration ultra, though less chemically robust rather than compared with the PVDF. As far as the membrane, so-called nominal membrane media, there are some available, very expensive. So, crucially in ultra pure water system, they do use some ion exchange media, though not the physical filter, the ion exchange. What about the stretch polyolefin? So it's inexpensive, chemical resistant, but application pre-filtration because the efficiency is not as good as the EPTF. Use cost and reverse matter more than precision or fine filtration. So core of modern liquid filtration media, polytetrafluoride. This is a bit different one. It's not EPTFA. Even though PTF itself, you can make the solution testing or different process to make the. It's nothing to do with the EPTFA. Nylon, PTFA, and then polyether sulfone is good one. So ceramic membrane and synthetic depth media made out of polypropylene and polymer, or activated carbon media. This is really good. Activated carbon media, removing chlorine, organic compound, and odor. See, in air filtration, the removing odor, we use a lot of activated carbon. This is common material. The sintered metal is, you can use it, but efficiency is low. But I believe the some of the applications they do use sintered metal, ion exchange, and biodegradable cellulose compound, tryptophan-based media. So, emerging for eco-friendly application, single-use system. Challenges and opportunity. What about the silk cellulose-based filtration material? Silk is quite the attractive material, but the if you look at the fiber size, is that really fine? Consider it as a fine material? Fine? I doubt it. When you compare with the EPTFE, the size-wise, the 2 nanometer, 2 micrometer, less than that. So silk is rather big compared with that. However, removal PFARs, this is solution state. They can actually remove it. Biochar-based media, carbon-rich the byproduct. Biochar is quite popular currently. In the liquid area, waste, especially the wastewater treatment. Graphene oxide enhance the filter. This one still under development somehow. The bottom here, smart filter. This is the quite getting popular. Sensor, now the sensor, the cost is getting lower and lower. So you can put the sensor. I don't know whether you notice or not. Some of the shot has a sensor in it. So once the heartbeat is to a certain level, it actually changes the color. It changes the color. So it actually warns you. Don't run that fast. You're gonna get stroke something. So currently the sensor cost is quite low. So everywhere they like to use sensors now. But they call it smart filter. I believe every field they have to look at the sensor. This is the future direction. So the living filtration membrane, self-healing water filtration technology. Also, 3D printing is getting popular. 3D printing is getting. Do you have it? 3D printing.
Yeah,
Yeah.
not in the department, in other department.
Yeah, this is getting popular. So, the company that I used to consult with, now all the frame, filter frame is using 3D printer. Making, yeah. This is quite. Also, natural ceramic membrane derived from the clay and zeolite. Recyclably used. I believe this is my last slide. So, huh? Any questions? In fact, this is my area of expertise on it. Which means I can do better than anyone else. Okay. If that is not.
I have one question. Like you talk about the biochar, no? Biochar. You are getting it from coir and other like natural fibers. Biochar.
Biochar raw material normally comes from China.
Okay. Yeah. But the main source is cellulosic material and all.
Correct.
After pyrolysis and all.
Yeah.
Now, how are you going to do that? Like, is it
you have to burn it. No, you have to burn it.
What I'm saying, you are using it, no? You are using it as a filter media. How are you going to use it? As a granular form or as some kind of
Activated carbon.
Yeah, kind of. It is a kind of activated carbon.
Yeah.
Whenever it is produced without the presence of oxygen.
Yeah.
Okay, at high heat.
Yeah.
And in India also a lot of biochars are available. Like activated carbon,
Yes.
that way.
Yeah. It's more like the activated carbon, similar to it.
It operates for absorption purpose. Okay, gaseous absorption. In the if you see that cartridge I had shown you, the outside there is a layer of filtering. Inside the activated carbon is there. So you are not getting smell from the water. Okay, so it absorbs some of the organic compound.
As a granular form?
Granular form.
It is granular. Correct.
So if you are using it in the mass, okay, so granular form is used. He is also working in the area with Ajay. And also it can be used in final form. There are pros and cons in both the cases. If it is a granular form, uniformity will be less. Okay, whenever you putting it. If it is in a powder form, uniformity will be more. So you can, it could be in a powder form, it could be in a granular form.
When you are using it, you are using it as inside a encasement or as a
multiple ways. For example, in cartridge, water resistant cartridge, that is a thick layer in the pipe. Okay, just after the outer fabric, inside you can have a thick layer of
column.
So that is the granular form you can use. But if it is for face mask, if it is for respiratory purpose, okay, so one can have a lot of that activated carbon inside one particular chamber. Okay, but if it is a simple respirator for industrial purpose, for example, gaseous environment, someone is working. So in that case also one can have layer of that material. Okay, whenever
Okay. Yeah.
two kinds of respirator is there: externally supplied And also you can take it, the air from